I'm continuing with this thrilling search of fundamental particles of matter. So, the outline of today's talk, I hopefully I would be able to touch these topic. Otherwise, I'm building up things actually rather slowly, so that I can give more and more relevant details along with this overview. So, firstly, I will again consider flavor symmetries, then how they lead to quark model, and possibly fundamental forces, and finally the standard model. So, as a reminder, what we learned from isospin group, that is SU2, special unitary group in two dimension. So, like ordinary spin and orbital angular momentum, their commutation relation, that is Lie algebra, is essentially the same, except that S is now replaced by I. So it is same mathematics but applied to different physical concepts. So states would be designated with eigenvalues of I3 and I square operator. I square is an example of Casimir operator. It has eigenvalues I and I plus 1, and I3 has eigenvalue small I. So this small I3 and I, these are used to designate the state. I is going from 0, half, 1, 3 by 2, whereas I3 has to go from minus I to I with of course successive difference of 1. We are dealing with quantum systems. So obviously the multiplicity of SU2 isospin multiplet is 2I plus 1, 1, 2, 3, 4. Actually, I am repeating these things because I will need them soon as I go further. So the lowest representation, that is doublet, it has two states with I half and I3 plus half, and also I half and I3 minus half. One can use this notation explicitly as a eigenket, or one can also use 1001 column vectors, or properly speaking, these are spanners, or you can simply write up and down. But we don't have to confuse isospin with ordinary spin. So what we can do, we can reserve this up and down for spin. So this is what I showed yesterday, that besides proton neutron near degeneracy, and also near degeneracy of pi plus pi 0 states, we have many particles which show this kind of a pattern. So we have isodoublets, two isodoublets, K plus K0, K0 bar, K minus. And same thing is happening for vector mesons too. And in case of baryon, we have two isodoublets for spin half baryon, and then one isodoublet for 3 by 2 plus particle. Plus means parity here. J is the total spin. And we also have isovector, pi plus pi 0 pi minus for pseudoscalar mesons, rho plus rho 0 rho minus for vector mesons, and sigma plus sigma 0 sigma minus for spin half baryon, and its heavy brothers for 3 by 2. We also have iso singlets, eta, omega, lambda, omega minus, and another isoscalar. We have very rare example of isoquartet. That means isospin value of 3 by 2, and there are 4 possibilities for I3 starting from minus 3 by 2 plus 3 by 2. This is a very unique kind of a delta state which carries spin 3 by 2. But the point here, I'm sure everybody is convinced that we have many isomultiplets which show isospin symmetry to a very large extent. In fact, isospin breaking is very small, of the order of 1 or 2%. But the interesting thing is that first of all, this isomultiplet structure is not finished here. I have given only the low-lying mesons and low-lying baryons, which are also called S-wave hadrons. But there are higher spin states, but incidentally, they also show the same kind of pattern. So the point is that all pseudoscalar meson of this kind, they come here. They show the structure of 8 or 9 particles. So we call it octet and singlet together. And same thing is we are seeing here. And then again an octet of the baryon. So these 8 particles carry spin half plus, and here we find 10 particles carry spin 3/2. So this itself is an indication that probably we can enlarge the symmetry and think of these states quite close, even though the mass breaking comes out to be of the order of 10 to 15%. But that is tolerable for the moment. So this idea Gelman and Lehman took seriously, and he extended the group, that is internal symmetry group SU2 to SU3. So again, I remind you that SU2 group is a mathematical structure. We can apply it anywhere we like. In fact, there are many kind of spins and isospin in particle physics literature. Same thing is also true for SU3. So first we are learning its mathematical and description. Then we will see how it is being exploited. There are many places where SU3 symmetry is used, not only in particle physics but also in other subjects like nuclear physics. So essentially, special unitary group in a three dimension is, mathematically speaking, is a group of special unitary 3x3 matrices. Say we call them U. And essentially, like SU2, SU3 is also nothing but rotations of complex vectors living in 2 or 3 dimensional complex vector space. So if you limit the dimensionality of the vector space to 2, then rotation of those complex vectors would be described by SU2. And if you choose 3 dimensional complex vector space, then the corresponding rotation group or unitary transformation group, more appropriately talking, that is SU3. So if you go for 4 dimensional or 5 dimensional or 6 dimensional, even to any large extent, if I remember in nuclear physics also, in interacting boson model, probably groups like SU12 or so are also used. So we have to live with these SUN kind of things. And the idea is this symmetry transformation is such that they preserve the length of the complex vector. It is exactly the same as rotation in ordinary 3 dimensional space. But incidentally, here the number of generators required is 8. So this you have to see it. It's not a difficult thing. Just to remember that we have imposed 2 conditions, that is a unitarity condition on U, as well as it's determined to be 1. So I can leave this as exercise to see that why we need only 8 things, because in 3x3 complex matrices, how many elements we have? 3 into 3, 9, 9 into 2, because every element has a real part as well as the complex part, 18. But then we will see that 18 will be reduced to 9 because of the unitarity condition, and one more condition, that is determined should be 1, will reduce 9 to 8. So that is how we find the requirement of 8 generator. In fact, there is a general formula for SUN group. Number of parameters on which the transformation depends is n square minus 1. Whereas for orthogonal group, it is n into n minus 1 over 2. Somewhere you might have done this thing while learning matrices, but same thing is being used here. So this generator of SU3 transformations, that is TA, similar to S, which we write as half sigma polymatrices. Here we write SU3 three generators as half into lambda A. Lambda A is the standard set of eight matrices, which are known as Gelman Gelman matrices. And if you remember poly matrices, we find the 2 cross 2 a part of this 3 are same as that. So in the same, if you play with the poly matrices by adding rows and column of zeros as a first or second or third, one can build up these things. This is a quick way of obtaining the Gelman matrices. So the point is, again, recall what I suggest. Whenever we are dealing with internal symmetric group or any symmetric group, we start with transformation. We look for its generators, and then what do? We go for its commutation relation. So commutation relation, that is technically called Lie algebra, tells you that commutator of any two generator or any Gell-Mann, for example, matrix here is nothing but expressible as a linear combination of the generators themselves. That is the simple thing. So out of these, see that only lambda 3 and lambda 8 are diagonal. All other are of diagonal elements, and their diagonal counterpart is 0. So this immediately suggests that these two can be used as eigen operator. By the way, you can also decide how many eigen operator we will have. It is simply for SU(n), it is just n minus 1. For SU2, it was 1. For SU3, it is 2. For SU4, this will be 3. So it is just n minus 1. It is technically called rank of the group. So these remaining 6 generators, they can be used to form 3 sets of shift operators. These shift operators are quite similar to L plus minus, which we have come across in while talking about angular momentum analysis. So here I just name them as I plus minus, U plus minus, and B plus minus. And then from these lambda matrices, we simply square them and add, or we make them cube and then add. In this way, one can generate 2 Casimir operator. This is analogous of L square in the orbital angular momentum analysis, whose eigenvalues give dimensions of the multiplet. Remember, the multiplicity in case of angular momentum is given by eigenvalue of the Casimir operator L square. L square eigenvalues are L into L plus 1, and using that L, we obtain the multiplicity as 2L plus 1. Same thing is true about spin and also for isospin. So in the same way, here we will be able to construct 2 Casimir operators. A question may arise in our mind. Is there a way to find out how many Casimir operators will be there? Simple. It is same as the rank of the group. The number of diagonal operators and number of Casimir operators are equal, which is rank of the group, and it is n minus 1 for SU(n) groups. But then suppose I take 2 Casimir operators and let me denote their eigenvalues as P and Q like L. Then obviously multiplicity will be some function of those P and Q eigenvalues of the Casimir operator. I'm not giving you the formula here. It's not very difficult. You can find out from the book. But the idea is that the eigenvalues of these 2 Casimir operators ultimately gives you multiplicity of the representation which are permitted by SU3. So in this way, we immediately find 1, 3, 3 star, 6, 6 star, 8, 10, 10 star. And by the way, there is a contrast here. If you look at the SU2 multiplicity, here you have I value 0, half, 1, and 3 by 2. But you see that multiplicity is just the counting number, because 1 stayed with isospin 0, 2 with half, and 3 with 1, 4 with 3 by 2. So in this case, all counting numbers are, or natural numbers are, allowed for multiplicity of the multiplets. But here we find that not all values are permitted. For example, 2, 4, 5, 7, 9 are missing. So this happens usually with every SU1 group or other groups. Not all dimensionalities are allowed. So there is a selection. One more thing, there is a 3 and 3 star. What does it mean? 3 star is actually conjugate to 3. Loosely speaking, not exactly. Somewhere it is something like contravariant and covariant vector, but the contexts are different, and we shouldn't confuse the thing because we are living in a complex vector space. So, if you like, you can call them 3 is representing eigencats and 3 stars are representing eigenbras. So maybe one can think of a dual space also. So that kind of understanding can be built up. After all, we are dealing with a complex vector spaces. So such things are likely to happen. Even here, I can take a moment to ask few questions, and maybe students can answer it. Would you like to write down the definition of a vectors? Often I hear about they are quantities which carry scalar and so, I mean magnitude and the direction. That is of course right, but incomplete. Proper definition of actually a vector is through its transformation law. For example, even in ordinary three-dimensional space, we decide how the vector component transform under rotation. Same thing we are doing in SU3 spaces or three-dimensional spaces also. So there is a certain manner in which the members of these multiplet mix together as a result of SU3 transformation. And one more thing which I will need later on is the how many ways we multiply two vectors. Often I again find only the answer given as a scalar product and the cross product. This is a incomplete answer. The proper understanding of multiplication of vectors come only when we go to the index form, and then we realize that suppose I have two vectors a and b with the components a I and b j. I multiply them together. Then I have three things to do. One, I can antisymmetrize the indices ij, because if you multiply ai with bj, what you will end up with? You will end up with a matrix. Now every child knows that a matrix, in general, matrix can be written down as a sum of symmetric and antisymmetric matrix. If you look at the components of antisymmetric matrix in three-dimensional case, we find these are nothing but components, the cross product. So we are still left with a symmetric matrix. Then what do? We reduce that matrix further by extracting the trace. And if you look at the trace, it is A1, B1, A2, B2, A3, B3, sum of these three terms. This is nothing but scalar product. So with this procedure of symmetrization and anti-symmetrization and taking trace out, we end up with three form of the products of two vectors. One is scalar product, the other is anti-symmetrized product, third is symmetrized traceless product. So that is the proper way of counting how many ways this thing is done. In fact, this becomes very important the soon I reach at a slide where law of commutation of states are to be understood. So a proper understanding of vector product of vectors come only when we go to the indices form. Anyhow, coming back to SU3 generator, we find that the states are designated. Obviously, we expect to use the eigenvalues of I3 operator and the lambda 8 generator representing hypercharge to designate the state. But note here, it's very important. Along with I3 y quantum numbers, which are eigenvalues of I3 and y, or lambda 3 and actually lambda 8, we find we also need to include I, and this I is coming from isospin, and it is related to the eigenvalue of the I square Casimir operator for SU2. So why it is important? It's really important because when you go for higher and higher groups, you have to be very sure which ladder you have taken. I mean, for example, SU3 can be built up as a direct generalization of SU2, but you can also obtain it from SO3. SO3 is a rotation group in three real dimension, which obviously form subset of three complex I mean dimensions. So in that way, SO3 wants to know through which particular rung of the ladder you have used. So therefore, it is required that we we include the subgroup components in this analysis. I3 is already included. So in that way, set of quantum numbers required to designate members of the ISO3 multiplied is I3 and Y. This is very important. So in this way, if you look at, first of all, realize that octet and baryons where 1, 8, and 10 represent, which are naturally provided by SO3. So that increases our faith that we are going in the right direction as far as understanding of internal symmetries of the hadron physics is concerned. So this is a natural candidate for as a group to describe these large number of hadrons. It works almost for all the spin states. So interestingly, because we have uh, generalized SU2 isospin to SU3, we have to understand how SU3 multiplets they contain various isospin multiplet with appropriate hypercharge, which is a new quantum number introduced by the SU3 group. So what we see here, this is a little mathematical. I'm widening it. Maybe at some other time, if Professor Shastri give me the opportunity, I will talk about details of the group theory in. And then you will see how we can use this. But at the moment, I can give you the hint. If you are aware of young diagrams, there are quick way of seeing how SU2 content of SU3 multiplets can be obtained. So what we find here is that octet contains a doublet with hypercharge 1 and another doublet with hypercharge -1 and a triplet, isotriplet and isoscalar with hypercharge 0. In the same way, this decuplet multiplet of SO3 contains a quartet, a isovector, isodoublet, isosinglet with hypercharge eigenvalues 1, 0, -1 and -2. Remember this and see how this match very well when I go to this. So these are the octets. So we have two doublets with a different hypercharge and a isovector and a isoscalar. So these 8 particle form octet pattern of pseudoscalar meson, and this remains singlet outside the game. In the same way, mesons, vector mesons also have two doublet isovector and isoscalar. And same thing is also true for baryon. We have two isodoublets and one isovector and one isoscalar. And but here we find for spin 3 by 2 particle, we have a quartet, we have a isovector, we have isodoublet and isosinglet. So in this way, we find that we are going in the right direction because SU2 isomultiplet content of SU3 representation match very well with the with the what we are doing. And this is the time here where I should also talk about the shift operators. We have learned about shift operators in angular momentum analysis, that is L plus minus. What it does, it changes the eigenvalue of the third component of angular momentum, that is M by 1 up or down, that is ladder operators. Same way we find here that in three sets of operator, we call them I plus minus, U plus minus, and V plus minus. And their action is very specific. For example, I plus minus do the same, actually same kind of a thing. It will increase or decrease the value of I3. But when we apply U plus minus 1, U plus minus and V plus minus, they act upon both hypercharge as well as the isospin. So they change the value of the isospin third component by half, but they change the value of hypercharge by one or actually -1. They always come in pair because if you want to go up the ladder, you have to come down also. So these are the action of the three shift operator. Technically, it is called root diagram of SO3 group. So what I've done here is I have plotted them on a I3y plane. I3y are the eigenvalues of lambda 3, lambda 8 generators to designate the state. So you see here that isospin raising lowering operator don't change hypercharge. They simply change I3 by +1 or -1. But if you look at U plus, we find here it decrease the value of I3 by half, but increase the value of Y by 1. Same thing is done in a reverse manner by U minus, whereas V plus increases the value of I3 as well as value of I3. So in this way, you have seen various weight diagram. I will show them again. Various states in that weight diagram are appropriately connected with the help of these six shift operators. I mean, for example, here, if you look at the pseudoscalar Meson octet, we find here that the particles on this axis are connected with the help of I plus minus operator, whereas particle on this axis we find they will be connected by the help of U plus minus, and particle on this side will be connected by V plus minus shift operators. So you see here how things are working. It is interesting also to note that along this diagonal line or slanted line, we find particles carrying the same charge. It is something similar here that on the horizontal axis we have shift operator given by I plus minus, but hypercharge value remain the same. Whereas along this axis, action of U plus and U minus operator will mix this state, but it keeps charge invariant. So sometimes in some books you may find the acidotic group also has actually is is said to have three SU2 groups. One is SU2 isospin group, the another is SU2 U spin group, and third is SU2 V spin group. Sometimes in some books you may find this kind of a thing. So you can do the same thing for the baryon octet also. We find here how various shift operator will take one state to to other ones. So here also you will find that along these slanted lines, the particle carry the same charge. And if you go for decouplet, we find here four particles, 3, 2, and 1, and all these particles also will be connected with with the shift operator. So that is how you can in a way exploit SU2, SU3 symmetries to relate various properties of these particle among one another. So in this way, I'm just giving the the final results, but I will show you someday how this can be obtained. First of all, SL3 could work exceedingly well as far as hadron classification, that is specifically 1, 8, and 10 multiplets chosen by the hadrons. In fact, Gell-Mann exploited this metric to predict the existence of omega, which was not there at that time, and he calculated its charge, its mass, very easily. In fact, charge is very easy to find because all particles in this axis have the same charge. So this is negative, negative, negative. So omega minus must be negative. And we also see that mass difference between sigma star and delta is nearly equal to cascade star and sigma star. So he even obtained that mathematically that spin 3 by 2 baryon decouplet baryon follow almost equal spacing rule as far as masses are concerned. How did he actually obtain it? It's very interesting because again we recall what happens to DJ. We know that hydrogen atom honor obviously SU2 symmetry. So if you that is spin symmetry, it means states with the different spin up and down orientation will have same energy eigenvalues as long as Hamiltonian of the hydrogen atom commutes with the spin operator. What happens when we apply magnetic field? magnetic field, the moment you apply, it will couple to the magnetic moment of the electron, say to the spin case. So magnetic moment due to spin will be dotted with magnetic field. Now mu dot B. B is in my hand. I can choose it any direction I like. So I choose Z direction. So that will bring only the third component of the magnetic moment. And what is the magnetic moment? It is given by essentially spin operator multiplied by E over 2m. That is all. EH or whatever you can say it. So essentially, what we find that the hydrogen degeneracy is broken by a potential term or Hamiltonian term, which is proportional to S3. And what is S3? S3 is already a member of spin generators. So often we will find even when symmetry breaking is there, it transforms as a special member of the, the generators of the group. Same thing happens in case of SU2 isospin, because isospin is broken by electromagnetic uh, interaction, and electromagnetic interaction involve charge. And you know that through Kalman-Nishijima formula, charge gets related to I3. That is third component of isospin. So it means the electromagnetic braking contribution to the strong to the hadron Hamiltonian should be proportional to I3 or Q, charge of the particle. In the same way, if you consider what is going to be the Hamiltonian for the hadron under the SO3 symmetric consideration, obviously it cannot be SO3 invariant. Why? Had it been SO3 invariant, then all particles belonging to one SO3 multiplet, say octet or decuplet, must have the same mass. Obviously, that is not true. So, therefore, in strong interaction, we find there are two terms. One, which gives major contribution to the particle masses, which is obeying SO3 symmetry, which I have just put it here. It's like a constant term to all the particles. But then there is also a term, though it is also strong interaction, but it is SO3 breaking term. And following the pattern of degeneracy breaking in case of hydrogen atom due to magnetic field and also due to electromagnetic interaction for the case of isospin symmetry, we presume that SO3 breaking Hamiltonian or potential term is proportional to eighth component of the lambda matrices, that is lambda 8. Just by using this, Gelman and Okobo derived these mass formulas for half half variant, which is quite reliable. And he also obtained equal spacing mass rule for spin 3/2. That is how he could predict the mass of the omega. And hardly with a difference of 2 MeV or so, the people experimentalists found the the existence of omega in some collision experiments. So that confirmed our faith that we are really on the right track. Besides that, SO3 and higher symmetry do much more. SO3 has the capacity to relate magnetic moment and even the strong electromagnetic and weak decay amplitudes involved in various decays of this hadron. For example, for the weak decay amplitude, Lee and Sogawara obtained a very well-known rule which relate weak decays of different iso multiplets, and the agreement is quite good. So when following this approach, people got excited. They generalized SO3 symmetries to SO4, SO5, SO6 to study further behavior of hadronic physics. They also tried to combine SO3 flavor symmetry, which we were talking about, with SO2 spin symmetry, and then put them in group SO6 together, 3 into 2 is 6. This naturally gave us two results. One, it automatically tells you that why should we have decoupled particle carrying 3/2 spin, and octet particle should have spin half as far as baryons are. baryons are actually concerned. Same thing you can do for the meson also. It will tell you that 35, which is the adjoint representation of SSS group, contains photoscalar octet as well as a vector octet in it. So not only that, it also gave the prediction of a ratio of proton and neutron magnetic moment to be minus 3 by 2, which is in close agreement with experimental value minus 1.46. It was basically a reminder. That is why I went a little fast. But then whenever we learn more, we always end up knowing that we don't know few other things. So our ignorance level also increases, and we are able to raise new and a new kind of question. We have just seen that there are many representation, many actual multipliers available as far as SO3 is concerned: 1, 3, 3 star, 6, 6 star, 8, and 10 star. Why nature seem to have only 1, 8, and 10 as a preference for the hadron etc. Why not 3 3 star, 6 6 star? So these questions were raised, and people had to give the answer. So answer was again given by Gell-Mann and Zweig. Of course, independently, they they suggested another layer of the onion. That is, these hadrons are not fundamental. They seem to be made up of quarks and, of course, and antiquarks. So this was the beauty, and these quarks are what fill up these three star. So three will be filled by quark, and 3 star will be filled by by this antiquark. And if you combine two quarks, QQ, then you will find these other multipliers are filled by filled. There are 6 and 6 star. So 6 and 6 star are filled by diquark states. 3 and 3 stars are filled by quarks and antiquarks respectively. So this was the idea. But even in the original paper of 1962 or so, we find Gell-Mann was bit hesitant. He was not even sure whether it is a physically real layer or these are just a mathematical modeling. But idea was very attractive, and very soon people got even convinced that that is right, and now we know that quarks are there. So what he suggested, that all mesons are essentially made up of quark anti-quark bonds, and three quarks together bond to give rise to baryons. So there is a three quark structure for the baryons and quark anti-quark structure for the meson. And since both quark and anti-quarks are present inside the meson, that is why, and you know that anti-quark is they are antiparticle of quark. So that is why all the mesons have their antiparticle within the same multiplet. In contrast, that is not true for the baryon. So if you want to have an antibaryon, you have to replace all the three quarks by three antiquark. Q bar structure will give you baryons. So just to give the example, now it is the 11th class material probably, that one can show that proton is actually made up of two up and one down quark, and this neutron is made up of one up and two down quark, whereas K plus meson is. One can keep on playing possibility. You can, as far as the structure of the head around 96, and these were named on stage. Up and down were taken quite analogy with isospin or spin up and down, so that is not much surprising. About stage, I have already given you in one of the early talks, that there are strange particles which were named strange because they revealed a strange behavior, and that was they were produced in strong interactions, but they decayed through the weak decays. Now these things are normal to every particle physicist, but in the beginning it was like a shock. So people expected the particle to decay through the same interaction it was produced in. So this behavior led to the concept of strangeness, and they just introduced a new quantum number that is called strangeness, which we have seen is essentially related to hypercharge. So this is what I could do yesterday. Now, formally talking about the properties of quarks. That is, these three quarks fill the lowest, that is the fundamental multiplet of SO3 group. So these are names is up, down, and stage here. Fractional charge. This is the deviation, and one shouldn't worry about charge quantization, because usually when we talk about charge quantization, we say that all the charges are integral multiple electron. I am just shifting the scale. Rather than talking about E, now I am saying that every charge is essentially an integral multiple of E by 3. So only the scale is shifted, but the idea of charge quantization is not damaged. All of these quarks carry spin half. So that way now they are quite similar to leptons, which also carry spin half. So both quarks as well as the lepton, they are fermions. And they carry fractional baryon number also, one third, one third, one third. And first two quark form isospin a doublet, isospin half, and third component half up quark, and the down quark is third component minus one. And strange quark does not carry any isospin, but strangeness is carried by this quark, that is minus one, whereas U and D do not have this quantum number. By the way, this is just a guess, because mass of a quark is still a very debatable issue. In fact, if you look into the literature, we will find two terms, sometimes even more than two terms used for the mass. Particularly in the case of quarks, we hear about constituent quark mass and current quark mass. Maybe at some other time I will talk about their difference. But this idea of 330 is essentially coming from this, that if a proton mass is given by three quarks and U and D are very close to each other, therefore the mass of your quark is roughly one third of the mass of the proton. So that is how you can estimate, and one can guess at the mass of the strange quark looking at the lambda particle. Lambda particle is actually made up of UDS. So just the mass difference of lambda from neutron, that can give you the idea between the for the mass difference between strange quark and the dyne quark. Take it as a small exercise. Just put arbitrarily uh, lambda particle mass minus the nucleon mass for spin half baryon is nothing but mass of the strange quark, and and of course minus sign and the U quark. So S minus U mass difference is expected to be the same as lambda minus R, and and different. There are reasons behind this formula, but at the moment I'm just asking you to do a numeric exercise just to get this idea. So this is how we guess it. But since so far nobody has seen free quarks, so nobody is really certain what is the true meaning of mass of the quark. So then we from here we go to antiparticle. So hmm, these antiquarks U bar, D bar, S bar, they now belong to conjugate representation of under SU3, and their properties can simply be obtained from them. What happens is that charge, baryon number, and third component of isospin and the strangeness. You might have heard that for every particle we have antiparticle, and charge of antiparticle is opposite to the charge of the particle. In fact, this statement is true not only for charge but for all internal quantum numbers like baryon number, isospin, third component, and strangeness, and many new quantum number would come, that is charm, bottom, top, etc. They will also change when you go from quark set to set of the antiquark. So we have D bar, U bar, S bar. Their name remain the same, their mass remain the same, but charges are now opposite. U quark had charge plus two third, now it has a minus one third, whereas D and S, they have the charge minus one third, they have now one third each. Spin remains the same because it is total spin. Baryon number, here we had one third, one third, one third. Now we have minus one third. In the same way, isospin remains same, but third component change. This is very important here. So U quark has third component isospin half. Now it has plus half. I think there is a slip here. Probably there is a slip. It should be plus half because isospin will also change. D should have plus half. Yeah, this okay. Yeah, there is a slip of sign here. So please change it to plus and change it to minus. And and the stageness the quantum number would also change. Minus one to one as far as this is concerned. These quantum numbers are required because when I will leave some of the problems for you to construct meson and baryon state and verify that their quantum numbers can be obtained as a sum of the quantum number of their constituent quarks antiquark. At that time you will need this table. So in this way one can see that mesons are formed just from quark and antiquark. They bind together. Just to give an example, suppose I combine U quark with anti-D quark. Its charge will be plus one because charge of this is 2/3, charge of D bar is also plus 1/3. So the net charge is plus one, and this is going to behave like pi plus. So pi plus is a composite state of these. In the same way, S bar D will form K0. It's a trivial thing that we have three quarks, three antiquarks so far. So possibilities are nine. So they will immediately fill the nine members of the octet and actually singlet. In the same way, one can think of the baryon made up of three quarks. For example, proton is three quark composite structure, and there is some kind of quanta which is being exchanged here. Technically, this is gluon, and we can also form anti baryon as made up of three antiquark. So far, it is a child game. Now, real questions come. And these are hard questions in the sense they have to be technically, and we should really appreciate the need of these questions because what is on just an idea. Unless we see them, unless we are able to understand various properties of hadrons in terms of quark wave function, only then we can give respectability to the hadron. Let us recall what we have done as far as electron states are concerned. How do we construct electron wave function? We treat atom, say hydrogen atom, as a bound state of proton and of course electron, and then this binding is done through Coulomb potential as a first part, and then we solve the problem. How do we solve it? We go to the Schrodinger equation and we apply method of partial waves, partial analysis, and separate the variables, and then go for the radial part because potential is spherically symmetric, and then we have the angular part, and which depends upon theta and phi, and that part is given by spherical harmonics, and the radial part is supposed to be Lagare polynomials. So combining everything together, we have this spatial part of the wave function. Is it sufficient? Oh, certainly not, because the moment we go from hydrogen to helium atom, we have to worry about identical character of particle. We have to worry about the spin degree of freedom, which incidentally is missing in the Schrodinger equation directly. But what do? We by hand introduce the spin. And how do we construct the spin part? All of you know that when we take two spin up and down, a spin up particle, we combine all possibilities, exploit angular momentum algebra to construct spin 1 and spin 0 state. I will remind you in the next actual slide. But the main part remains the same, that overall wave function is given by direct product of spatial part of the wave function and spin part of the wave function. Interestingly, spin part is easy to calculate, easy to combine just by following the law of collapse-Gordon actually coefficient. But Coulomb part, the spatial part takes time. We carefully handle the equation, separate the variable, handle the angle part, and finally the radial part. Now the question is, can we do the same for mesons? After all, mesons and baryons are also bound state of quarks. That is the attempt we are moving towards. But we have to be careful. First of all, let me give you these actual descriptions are given very nicely in particle physics by by Griffith, and I hope as Professor Shastri told me, you people are following that book. It is one of the best books written for particle physics, especially from teaching point of view. So in that book, what he does, he takes up hydrogen atom, replace the proton by a positron. So the moment you do it, now both, because there is a difference between hydrogen atom and the so-called positronium. In hydrogen atom, the heavy nucleus is at the center and electron is moving along. But when you go to positronium, you replace the actually proton by the positron. Now it is a two-body problem with the same mass. We have to be careful. So center of mass we have to separate out. So the reduced mass will not be just equal to the mass of the electron. It is going to be half of the mass of the electron. So new considerations start coming in with at the moment go further. But we also have to remember we are dealing with fermionic system. Why? Because electron positron both are falling, both are having a spin half. So therefore, its wave function should be overall antisymmetric. So that gave rise to two possibility. The spin part may be symmetric and antisymmetric. I'm just reminding you the helium atom problem. So the spatial part may be symmetric and antisymmetric. That is how ortho and para states of the helium is genetic. Exactly similar treatment can be done for positonium, which is a bound state of electron and positron. The last step is what you have to do is replace electron and positron by quarks and antiquarks. The game seems to be simple. It looks we have solved the problem. It's really not actually solved because the reason is in case of hydrogen atom and positonium problem, we know potential very well. It is just one over R kind of a potential, Coulomb potential. We can play the same game. Can we do the same thing for you? No, we can't do it. This is one of the great actually setback when we go to the quark model. We don't know the potential responsible for which is controlling the binding of quarks and antiquarks. So what we can do, either we can dual models. So that is why we call quark model. And in that model, we assume various kind of potentials to try and actually play with it. But even then, life is not that easy because particularly for the low mass quarks, that is U, D, and S, system is not really obeyed by Schrodinger equation. Is described by Schrodinger equation. These quarks, very low mass quarks, behave relativistically, so one has to go for the relativistic quark model also. So I'm going into the little technicalities, but I will not go into too much detail of the spatial part. But somehow we believe the spatial part can be obtained by assuming some kind of potential. However, most of the time we will be assuming potential to be spherically symmetric. And as long as potential is spherically symmetric, that is central, it does not depend upon theta and phi. Luckily, its angular part is given by spherical harmonics. That is a big relief. But now the wave function is not just the product of spatial part and the spin part. Now the wave function, that is Meson wave function, say for example, it is going to be product of spatial part of the wave function, which is controlled by the potential. Spin part, which is quite similar to what we have seen in case of helium atom. And then we will have another part of the wave function, that is called flavor wave function, that is controlled by SU3. So things are now little formal. We have to go slowly in this direction. And who knows, perhaps more things will come, and probably you might have guessed I'm actually referring to color part of the wave function. But so how do we play this game? How do we construct spin wave function and quark flavor wave function for these composite states? So that is the issue. For that purpose, let me remind you what we did for the case of addition of angular momentum. Consider a system of particles, any particle, and this is all of us probably have done it in our master degree somewhere. That is addition of angular momentum. How do we do it? Suppose we have two angular J and JB associated with two particles. To limit, to begin with, first we limit to two particle state, because three particle systems are going to be more complicated. So seeing that, I restrict the system of two particle. Each of them carry angular momentum. Sorry, this, yeah, J JB. This could be spin angular momentum. It could be orbital. It could be total angular momentum. That is not the point. Any angular momentum you choose, you just do it. So what do? We obviously know that each of those particles will have eigenstates given by J, Ma, and JB. There's a comma here, and just put them together. That should be able to describe the system. But is it the whole story? We also know that is not the whole story, because when we have two particles angular momentum, they add together to give rise to J. This J values go from mod of J minus JB to J plus JB with appropriate quantization. And the third component of J, that is M, is simply the sum of third component of J and JB. So in this way, we find that this JM candidate also a good candidate to describe the particle. Why? Because JM also obey the same Lie algebra, that means same set of commutation relation, which are obeyed by J and JB. And if you're smart, you can see it is nothing but change of the basis. Doesn't matter very much. But the point is, these states, JM state, are obtained as a linear combination of states which are given here. So it is as simple as that. And these linear combinations involve certain coefficients of these terms. Those are technically called Clash-Gordon coefficient. And I know that we have this thing in our master's syllabus as far as the treatment of anglomentas are concerned. And these Clash-Gordon coefficients are very important. One comment that they are actually consequence of structure constants which appear in commutation relation. But ultimately, these coefficients are what will give you the physics. These are very important, and ultimately, when we apply Wigner-Riccard theorem to obtain various physical results, these Collapse-Gordon coefficient will actually give us the physical results. So it's really very important. So just as a quick reminder, did it. So what do we do? Exactly the same thing. Whatever I have given here is a general, and now I am giving a special case. And there is a similarity between spin and isospin, actually wave functions. So because suppose I start with two particle space, that is both carry spin half, then these are the four possibilities. Now, it carries the third component 1, but this carries third component 0, and this carries third component 0, and this carries minus 1. So these state have something common. They have third component of S3 equal to 0. So there is a possibility they may superpose. And we handle it carefully, because we know that when we add two spin half particle, the net spin is going to be either the difference or sum, that is 1 and 0. And this 1 0 states will have these four possibilities: 1 1 1 0 1 1 minus 1. These are the third component. So these are spin vector, and these are spin scalars. So these immediately go with them, because they are only one candidate. Here the third component simply added. So 1 1 is just 2 up, and 1 minus is 2 down. But this 1 0 0, so the state come out to be the combination of up down and down up with plus and minus sign, and these are root which is there for the as the normalization factor. So precisely these 1 over root 2 here and 1 over root 2 here with plus minus sign, these are nothing but Clark-Gordon coefficient. They tell you how states are combined to give us the physical states. So in that way, this is essentially a change of basis. And now, as we have already seen that isospin treatment is similar to spin, what you have to do is simply replace up by U and down by D. That is all you have to do. So there is a one-to-one correspondence here. So suppose I want to construct two quarks state, then in general there will be UU, UD, DU, DD by state. Again, I follow the addition law. So the total isospin of two quark state should be either 1 or 0, and it will have these four possibilities. these four possibilities will be connected with these four states in this manner. Same CG coefficient appear here. When you go to quark wave function, suppose I consider diquark seriously, then diquark will have isospin 1 or 0, but also quark carries spin half. So therefore, diquark state will also carry spin and 1, 0. So one can write down SU2, the one can write down the wave function of diquark state as a direct product of isospin wave functions given here and and ordinary spin actual wave function given here. Just to give you the example, suppose I consider the iso vector diquark state made up of u quark. It can have spin 1. So in that case, this u up and u up state will describe diquark state made up of two u quarks with iso with ordinary spin 1 and third component 1. So u up will give you that. So that is how the two kind of actually wave functions are combined together. So with this, what we do, this is what we understand normally. But group theoretically, we simply change the language. What do? We don't say half plus half goes to 1 into 1 and 0. We simply write in terms of their multiplicity. So what is the multiplicity of spin half or isospin half? That is, so 2 into 2 will give you four possibilities, which we have here. And these 2 and 1 are reduced to as sum of 3 and 1. 3 for isovector and 1 for isoscalar. So one can see it through group theory formally also, but that was a trivial case. So such kind of reduction of direct product of SUN multipliers is called a reduction of direct product. So in that way, technically we say 1, 2, 3 form the irreducible multiplet or representation of SU2 group. So when you combine 2 into 2, we have 4, and this 4 is which actually reduced to 3 plus 1, and this is known as Clapeyron-Gordon series. Suppose we want to construct three particle states, particularly suppose I am trying to build up spin wave function of baryons. Then we know there are three quarks, each carries spin 3 by 2, sorry, spin half. So 2 into 2 and 2, 8 possibilities will be broken into 2 and 2 and 4. This 4 is for the spin 3 by 2 states, and these are for the spin half states. So in this way, this language of reduction of direct product we have to understand. If we have seen this procedure for SU3 and higher group, this reduction is little technical. But believing our results given here, one can see that suppose you want to construct mesons out of quark and quark. Quark belong to 3, antiquark belong to 3 star. So 3 into 3 gives you 9 possibilities, but it is formally done here, and we see that this direct product of 3 and 3 star is automatically reduced to 1 plus 8. So that justifies why meson should follow the pattern of singleton octet. So quark model in this way explain the observed hadron spectra. Suppose you go to for a baryon, then we have 3 into 3 into 3, 27 possibilities. Technically, mathematically, it is directed to be reduced to sum of 1, 8, 8, and 10. So that is why we have octet of baryons and decouplet of the baryon. Rarely we also find singlet of the baryon. So in this way, quark model explain very nicely the observed hadron spectra. So with this, we come here. By the way, Amit, say how much time we have? Hello?
Yes, sir. Sir, can we stop here? Actually,
yeah,
we have completed.
I think we should. I think we should.
Yeah.
Because this matter is going to be little technical, and I will advise students to go through these actually yesterday and
yes, sir.
Carefully, so that they can appreciate the further.
Right, sir.
So I take leave.
Okay. Yes, sir. Thank you very much, sir. Thank you so much. And so all students are requested to go through the video lectures of yesterday and today, which will be uploaded today. And I'll also upload the PDFs for the same. Kindly go through the video and meet at 4 o'clock. Okay, sir.